female employees, despite this discrimination being unlawful under the Civil Rights Act of 1964. Tesla has faced a number of serious allegations of racism and sexism at its Buffalo and Fremont plants. Companies that allow bias, discrimination, and harassment in their workplaces are at risk for unnecessary legal, brand, financial, and human capital issues. Support for this resolution is warranted for the following 5 reasons. 1. Research shows that companies benefit from diverse and inclusive workplaces. 2. Corporate policies that allow harassment and discrimination risk investors' capital. 3. The use of arbitration exposes investors to an unknown level of risk. 4. Broad concerns exist with respect to fair treatment in Tesla workplace, and Tesla employees have alleged harassment and discrimination on the basis of both race and gender. Tesla, a company investors love for its innovation, leadership, and wise moat, is increasingly lagging behind its peers in its disclosure related to workplace diversity, equity, and inclusion. Unlike the forward-thinking and innovation in its extraordinary product lines, Tesla has not shown proactive leadership in building a positive company culture or in addressing concerns about its workplace practices. In these material issues, Tesla lags behind its technology and automotive competitors. The use of arbitration limits employees' remedies for wrongdoing, precludes employees from suing in court, and often keeps underlying facts, misconduct, or case outcomes secret, therefore preventing employees from learning about and acting on shared concerns. Simply stated, arbitration allows bad corporate behavior, like bias, harassment, and discrimination to continue, hidden from employees and investors. To maintain Tesla's wide moat, it is essential that the board seriously assess the implications of the use of arbitration and that Tesla begin to take seriously the need to ensure a fair, equitable, positive, and inclusive workplace. Thank you.
Thank you, Ms. Hall. Our 4th and final proposal is an advisory vote regarding reporting on human rights. Our board has recommended that stockholders vote against this proposal. This proposal comes to us from the Sisters of Good Shepherd, New York Province, whose representative, Terrence Collingsworth, is on the line to present today. Mr. Collingsworth, I would like to invite you to speak now. You have 3 minutes for your proposal.
Thank you. I'm Terry Collingsworth, Executive Director of the International Rights Advocates. I'm here representing the Sisters of Good Shepherd, New York Province, to present item 7 on human rights disclosure, which calls upon Tesla to issue a report to describe board oversight of human rights and its human rights due diligence process, including systems to provide meaningful remedies when human rights impacts occur. Tesla faces serious human rights issues, and failure to establish a culture of respect for human rights will expose Tesla to new liability issues and significant reputational injury, all of which will have a material impact on the company and its shareholders. The need to set a new course for human rights compliance at Tesla is glaring. Here are 5 examples of human rights violations occurring now in Tesla's operations. Racism, sexual harassment, and disregard for human safety and dignity harm workers at the Gigafactory 2 in Buffalo, New York every single day, and those workers urge you to remember their experiences in your vote. Tesla is experiencing serious labor relations issues at its production facilities and is actively discouraging union organizing. Workers are being exposed to COVID-19 and then are facing retaliation when they ask for greater protections. There are numerous worker health and safety violations as well as wage and hour issues. And finally, there are serious, even deadly human rights violations occurring in Tesla's global supply chains. On this last issue, my organization brought the pending suit against Tesla for using cobalt mined in the Democratic Republic of Congo by young children. I personally met young boys who lost limbs or were paralyzed in cobalt tunnel collapses. Tesla sources cobalt from these very mines, and its claim to have, quote, zero tolerance for child labor in its supplier code of conduct is simply not true. Tesla is not only tolerating child labor in its cobalt supply chain, it is tolerating the death and maiming of young child miners. This demonstrates why the company must circle back and begin a process to report on its treatment of human rights issues as requested in this proposal. I think consumers will have zero tolerance for a company that is exposed as being indifferent to killing and maiming child miners. We are hopeful that Tesla's innovative spirit can be brought to bear on making human rights a priority at the company. For example, if Elon Musk cared about implementing a zero-tolerance child labor policy, instead of having a useless paper policy, Tesla could employ satellites or drones at every mine it sources from to actually monitor child labor. I encourage all Tesla shareholders to vote for Item 7, Human Rights Disclosure. Thank you for your attention.
Thank you, Mr. Collinsworth. At this time, I'd like to thank our stockholders for all of their active participation in today's meeting and for those who just presented on the line. I'd also like to read some of the comments that have been submitted by you over the course of the meeting. The first comment comes from Michael Overbaugh. I take great pride in the fact that we haven't had to stoop to the level of what advertising represents to get where we are today. I'd hate to give in to that kind of temptation now when we're so close to becoming a household name that's based solely on our merit alone. But if assets do end up having to be set aside for marketing, I'd like to suggest that rather than shoving ads down the customers' throats, we establish some sort of hardcore nationwide campaign and event with the goal of getting as many people as possible behind the wheel of a Tesla for an introduction drive. It's well known how far just doing that alone goes to converting people into fans. A line I recently ran across says, "You can talk all about the specs as much as you want, but when it comes to buying a car, what ultimately puts butts in seats is the feeling that the vehicle gives you." By demonstrating that Tesla clearly has both the specs and the feeling, what more needs saying? Our second comment comes from the United Steelworkers on behalf of the Clean Air Now Coalition of Western New York by Sabrina Liu. Proposal, and it reads as follows. Proposals 6 and 7, up for vote this year, are the results of widespread concern about mistreatment of Tesla workers at U.S. factories and across the supply chain. It is clear that Tesla is not interested in addressing the harm they have caused to their workers, as their board is advising shareholders to vote against the proposal. We're urging all shareholders to vote in favor of Proposals 6 and 7. And on behalf of our workers at the United Steelworkers here in Western New York, and for Tesla employees across the country and across the global supply chain, while this doesn't repair the harm that's already been caused to countless employees, nor repair harm to children and communities forced into slave labor in the DRC, they represent steps towards a more just workplace at Tesla. This concludes all of the comments. Thank you all for your participation in the comments. We'll now have a final opportunity for any of you to submit proxies in order for them to be counted. So I'll pause and wait for a moment for you to do that. Okay, I declare that the polls are now closed. So based on the proxies that we have previously received, I'd like to announce on a preliminary basis that our stockholders have approved the recommendations of Tesla's board on all agenda items, other than the stockholder proposal for an advisory vote regarding simple majority voting in our governing documents. After the final tabulation is completed, we'll formally announce the results of the voting by filing a Form 8K with the SEC within 4 business days of today. This now concludes the official business of Tesla's 2020 annual stockholders meeting, which is now adjourned. Next, we will have a company update and a year in review presented by Elon, and then we will start our Battery Day event. During the course of those following sessions, we may discuss our business outlook and make forward-looking statements. Such statements are predictions based on our current expectations. Actual events or results could materially differ due to a number of risks and uncertainties, including those disclosed in our most recent 10-Q filed with the SEC. These forward-looking statements represent our views as of today. They shouldn't be relied on after today, and we disclaim any obligation to update them after today as well. We will now continue with the company update and year in review, and it's my pleasure to introduce Tesla co-founder and CEO, Mr. Elon Musk.
Hey everyone. Well, I mean, this is definitely a new approach. We got the Tesla drive-in movie theater, basically. It's good to see everyone. It's a little hard to read the room with everyone being in cars, but it's it's the only way we could do it. So hopefully it's cool, and hopefully you can hear me. Can you guys hear me? Okay. All right, great. All right, well, thanks for coming. I think it's been an incredible year, and I'd like to thank you for your support through tough times, good times. It's been great. Really appreciate everyone who's put their hard-earned money into Tesla, and I think it's worked out pretty well. This has been a good year, and I think there's many good years to come. So I'll go through the sort of the shareholder presentation, I think, fairly quickly, because the sort of real main event here is Battery Day. So, really, I'm just going through a recap of what's happened over the past year or so. I think starting from in terms of our ability to create a factory, huge kudos to the Tesla Shanghai team for being able to go from literally a dirt pile to volume production in 15 months. It's like, damn. Yeah. So, and I think something that's really quite noteworthy here is Tesla is the only foreign manufacturer to have a 100% owned factory in China. So this is often not well understood or not appreciated, but to have the only 100% owned foreign factory in China is a really big deal, and it's paying huge dividends here. So we really wouldn't have the results that we have had this year without the great efforts of the Tesla China team. So I'm super appreciative of that. And we'll see the Shanghai factory continue to scale quite a bit from where it is right now. I think we really could expect that to be, over time, a factory that produces over 1 million vehicles a year. Yeah, it's cool. So let's see. So we also reached in the past year volume production of the Model Y, and this was the smoothest launch that we've ever had. So I think we're definitely getting better at new vehicle launches and building factories and scaling production. As you've heard me say before, it's the hardest thing is scaling production, especially of a new technology. It's insanely difficult. Making a prototype is relatively easy. And if I think of, like, what is the real achievement of Tesla in sort of car company terms, it's like it wasn't making sort of exciting prototypes. It was that Tesla was really the first company in about a century in the US the first U.S. company in the U.S. to reach volume production and be sustainably profitable. Like the crazy thing is this has really not happened in 100 years. That's the actual super hard part. And we now have 4 vehicles in volume production, S3XY. So also the toughest joke, I think maybe ever. It was a very difficult joke to make. So we also introduced the lowest cost solar in the US. It's only $1.49 a watt. And we really just simplified the whole value chain. So reduced sales and advertising, got rid of a bunch of unnecessary costs, and really are just relying upon the fact that it's just the lowest cost, most efficient solar in the US, providing both retrofit and the solar glass roof, which I think is a really great product, a hard product to make work, but it will be a major product line in the future. And we also got 4 consecutive quarters of GAAP profitability, which was very difficult. Yeah. So, and certainly a testament to the hard work of people at Tesla. I mean, to do this in extremely difficult times against a wide range of adverse circumstances was insanely hard, but we got it done. So, and I think the future is looking like I think very promising from sort of an annual profitability standpoint. So, in order to achieve, in order to sort of do well financially, you really need economies of scale, and you need ideally the best technology. And I think we had the best technology for a while, but now we are also achieving economies of scale. So, and we're also rapidly improving autonomy, which is a massive value add to each car. So, you know, I think the value of Tesla is going to be like total, just on the vehicle side, total vehicles produced times the value of autonomy. That's a way to think about the future value of Tesla. We also have consistent free cash flow generation. This is really important for growth. And a key element here is tightening up the time from when a car is ordered to when it is built and delivered. So for a company that's growing rapidly, it's extremely important to tighten the supply chain and to have, from when parts arrive, put it into a car very quickly and deliver the car very quickly to the customer. And if you can do that inside the sort of your kind of payables timeline, then the faster you grow, the more cash you have. Or conversely, if you're unable to do it within your payables timeline, the faster you grow, the less money you will have, which is obviously bad. It's for a capital-intensive situation. So just tightening up and having the parts move very quickly to the factory, put it in a car, get it to a customer, makes a massive difference to cash flow generation. And I mean, that's why it's extremely important to have a factory in each continent. Because if you don't at least have a factory in the continent, it is impossible to achieve this. So having a factory in China that's able to serve China, and then you know, soon many other countries in the region, will be key to us tightening that total sort of chain of cash flow and getting it, essentially the faster we grow, the more cash. This is really important. That's also why it's important to have Giga Berlin complete, because then we'll have a factory in China, a factory in the U.S., and soon a second factory in the U.S. in Austin, and a factory in Europe. And I mean, even if for Giga Texas in Austin, even if we had exactly the same costs as in California, it would still be advantageous to do it there because it's roughly 2/3 of the way across the U.S. So in terms of delivering cars to the central U.S. and to the East Coast, it's just faster, costs less, and it fundamentally improves our economics. So I think this is also maybe something that's not fully appreciated of just how important it is to have a factory at least on the continent or reasonably close to where the end customers is, so you can tighten that whole chain. Industry performance. We've you know, while the rest of industry has gone down, Tesla has gone up. I think this speaks to thanks. And so I'd like to thank all the customers for taking a chance on Tesla and buying our product, and really hope you're enjoying it. This is really, our sales, as Elle was saying, really grow by word of mouth. So this is really, I think, a very pure, it's very pure in the sense that it's like, it's growing on the basis of existing owners recommending it to new customers. This is really, I think, a good way to grow. And then in 2019, we had 50% growth. And I think we'll do really pretty well in 2020. Probably somewhere between 30 to 40% growth, despite a lot of very difficult circumstances. I mean, there's so many, probably, pandemic, wildfires, is like a whole bunch of difficult production issues. But thanks to the hard work of the Tesla team and a lot of innovative approaches to overcoming issues, we're able to still see significant growth in one of the most difficult, in fact, I say probably the most difficult year of Tesla's existence. So, and we also published our extended impact report. At Tesla, we try very hard to do the right thing. If the right thing does not happen, it's just because we maybe made a mistake or weren't aware of it. But we always try to do the right thing as to the best of our ability, and then we published the extended impact report to show, just a sort of a self-examination of, okay, what are we doing right, what are we doing wrong, what can we do better in the future. We're definitely trying to accomplish the most good, and so, if we occasionally make a mistake, we work quickly to fix it and do the right thing. So. It's worth looking at like the average life cycle emissions in the U.S. And just how much better a Tesla is or an electric car than any other than any kind of gasoline car. And what we'll talk about in the battery day is also just how much the grids around the world and actually especially in the U.S. are greening. It's actually much faster than I think people realize. The U.S. is moving towards sustainable energy. And so as we move more and more to sustainable energy, then effectively you end up building the solar factories and the car factories themselves with solar. Over time you do, or with sustainable energy. Over time you'll even mine with sustainable energy, and eventually it will get to an effective emissions of 0. So that's where things will end up. Yeah. So. We also have safety at the core of our design. The Tesla cars are the safest cars ever designed. We have the lowest probability of injury of any cars ever tested by the U.S. government, and that's just passive safety. When you add active safety into that, it's even better. It's really, if safety is important to you, which obviously it is, the safest car you could drive is a Tesla. So. I think some people aren't aware of this, but it's really, safety is paramount. It is actually the #1 design objective when we build a Tesla is safety. Our factories are also becoming safer, and if you look at the sort of accidents per total vehicle made, it's dramatically better than in the past, and it's already better than industry average, and we're confident we can get it to the best in the auto industry. Autopilot functionality continues to improve, and you can see it in the safety report that we publish every quarter. It's just getting better and better. The U.S. average for collisions is at roughly 2.1 per million miles, and with autopilot engaged, it's 0.3. I mean, this is a profound difference. It really massive, and this will get even better. So. We're confident that over time we can get the probability of an accident, especially the probability of injury, to 10 times better than the industry average, like an order of magnitude better. So that's just a lot of lives saved and a lot of injuries avoided. So that's a huge priority for us. On the autopilot front. I think it's kind of hard for people to judge the progress of autopilot. Like I'm driving. As a matter of course, I've always done this. I drive the bleeding edge alpha build of autopilot, And so I sort of have insight into what is going on. Previously, about a couple of years ago, we were kind of stuck in a local maximum. So we were improving, but like the improvements kind of started tailing off and just not getting where they needed to be. We were quite close to sort of getting trapped in a local maximum. And so we had to do a fundamental rewrite of the entire autopilot software stack, and all of the labeling software as well. So we're now labeling in 3D video. So this is hugely different from previously where we were labeling essentially a bunch of single images from the 8 cameras, and they would be labeled at different times by different people. And some of the labels, you literally can't tell what it is you're labeling. So it basically made it sort of in some cases impossible to label, and the labels had a lot of errors. Now, with our new labeling tools, we label it in video. So we actually label entire video segments, and the system, so you get basically a surround video thing to label, and with the surround video and with time. So it's now taking all cameras simultaneously, and looking at how the images change over time and labeling that, and then the sophistication of the neural nets in the car and the overall logic in the car has improved dramatically. I think we'll hopefully release a private beta of Autopilot, or the full self-driving version of Autopilot, in I think a month or so, and then people will really understand just the magnitude of the change. It's profound. So yeah. Anyway, so you'll see it's just like a hell of a step change. But because we had to rewrite everything, labeling software, just the entire code base, it took us quite a while, and the sort of new sort of, I call it like 4D in the sense that it's 3 dimensions plus time. It's just taken us a while to rewrite everything, and so you'll see what it's like. It's amazing. Yeah, it's just clearly going to work. In Tesla core competencies, we've got engineering, obviously. But also manufacturing. I think manufacturing is underappreciated in general, and the difficulty of designing the machine that makes the machine is vastly harder than the machine itself. So, the designing, like making a Model 3 or Model Y or a Cybertruck prototype is really quite trivial compared to designing the factory that makes it. Especially if it's new technology and you want to use new manufacturing methods, it's just at least 10 to 100 times harder to do the factory than the prototype. And that's why you see a lot of companies out there or startups, they'll bring out a prototype, but they just can't get it over the hump for manufacturing, because manufacturing of new technology especially is the hardest thing by far. Like basically the prototype is at best 10% of the difficulty and probably closer to 1%. And then software. Tesla is both a hardware and a software company. So a huge percentage of our engineers are actually software engineers. And you can think of our car as kind of like a laptop on wheels. And so software is incredibly important. And so not just in the car, but also in the factory. So the factory software is extremely important. Just software in general. These are fundamental. These are the 3 critical areas that are needed to make for an awesome company. So, yeah. So we have now we'll soon have 3 new factories, incremental, on, well, we have one already, on 3 different continents. Shanghai, we're expanding to Shanghai with the second phase. Berlin is making rapid progress, and Texas is making even faster progress. So, yeah. With each factory, what we're trying to do is also improve the manufacturing technology. So it's in some cases, like the Model Y made in Berlin might look the same, but it actually is made in a much more efficient way. And yeah, we'll talk about that later in the battery presentation. Yeah, launched Megapack. It's a 3 megawatt hours all-in-one energy storage solution. So it's been great overall. Yeah. All right, and I think that's basically it. Right. All right. Thank you. All right. Well, thanks everyone for coming, and we'll be back in a little bit to go through the battery stuff. And there's a little bit more in addition to the battery stuff. We got a few extras as well. So I think you'll really like what we have to say on batteries. The battery stuff we're going to talk about is truly revolutionary and essential to Tesla's goal. The fundamental good of Tesla. It's like if you look back in history and say what good did Tesla do? The good will be to by how many years did we accelerate sustainable energy? That's like the true metric of success. It matters if sustainable energy happens faster or slower, and so that's really like how I think about Tesla and how we should sort of assess our progress. By how many years did we accelerate sustainable energy? And what we're going to talk about with batteries and a few other things will really explain how we're going to make a step change improvement in the acceleration of sustainable energy. Thank you.
Hi, folks. That was great. We're going to take a short break before we begin the Battery Day event. So stay tuned. If you're local and here in the audience today, you can feel free to get out of the cars and stretch your legs. But try to stay near the cars because we're going to begin promptly in a little bit. See you soon.
Hello, everyone. Sure. Thanks, Elon. Oh, hi. I'm Drew Baglino, SVP of Powertrain and Energy Engineering at Tesla, and I'm incredibly excited to talk about what we've been doing at batteries here at Tesla.
Great. So let's see. You got the clicker.
Yeah, I've got the clicker. Yeah.
Okay. I'll take it first, perhaps.
Sure.
So obviously the issues we're facing are very serious. With climate change, and we're experiencing these issues on a day-to-day basis. It's incredibly important we accelerate the advent of sustainable energy. Time really matters. This presentation is about accelerating the time to sustainable energy. So the past 5 years were the hottest on record. We have what looks like a wall for CO2 ppm. It's obviously, this time is not like the past. It's really important that we take action. Running this climate experiment is insane. So,
especially when it's just a transitory one anyway.
Yes.
We're going to run out of these fossil fuels. Let's just move to the future and not run this experiment any longer.
Yeah. Talk a bit louder.
You got it.
Okay. So anyway, there is a lot of good news, though. A lot of people may not be aware that wind and solar comprise 75% of new electricity capacity in the U.S. this year. So this is a really major. So the grid is going sustainable very, very quickly. Now, it's also worth noting that the length of time that power plants last is on the order of 25 years. So even if 100% of energy generation was sustainable, it would still take 25 years to convert the grid. And it's also worth noting that in the past 10 years, power production from coal has dropped in half. So it went from 46% of electricity in 2010 to 23% in 2020. So this is a massive improvement. So good things are happening on a lot of levels. We just need to go faster. So in terms of Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generated. So I think solar is sometimes underweighted at Tesla, but it is a massive part of our future. The three parts of a sustainable energy future are sustainable energy generation, storage, and electric vehicles. So we intend to play a significant role in all three. So to accelerate the transition to sustainable energy, we must produce more EVs that need to be affordable, and a lot more energy storage, while building factories faster and with far less investment. So goal number one is a terawatt-hour scale battery production. So tera is the new giga, and a terawatt is 1,000 times more than a gigawatt. So we used to talk in terms of gigawatts. In the future, we'll be talking in terms of terawatt hours. So this is what's needed in order to transition the world to sustainability.
Yeah, and you can see we're talking about 100x growth in batteries for electric vehicles to achieve this mission. And we are going to get there. It's just a matter of how fast, and our intention is to accelerate it.
Yeah. You basically need on the order of roughly 10 terawatt hours a year of battery production to transition the global fleet of vehicles to electric.
And the average vehicle lasts 15 years, so we're talking about 150 terawatt hours, give or take, to transition the whole all vehicles of all types to electric.
Yeah, so it's a lot of batteries, basically. Yeah, so.
And then on the grid side, we have a similar mountain to climb, 1,600 times growth from today's grid batteries to go 100% renewable on the grid, and to take all of the existing heating fossil fuel uses in homes and businesses 100% electric.
Yeah, and this number, I think, might grow even more, as the world economy matures and as countries with high populations industrialize, we could see this number be even more. But let's say it's like roughly 20 to 25 terawatt hours per year, sustained for 15 to 25 years to transition the world to renewable. This is a lot.
Yeah.
So today's batteries cannot scale fast enough. They're just too small. For Giga Nevada, 150 gigawatt hours per year is like what we probably expect to make out of there. But this is really pretty small in the grand scheme of things. That's only 0.15 terawatt hours. And it costs too much. So
We would need 135 fully built out Nevada gigafactories to achieve 20 terawatt hours a year. It's not scalable enough of a solution. We need a dramatic rethink of the cell manufacturing system to scale as fast as we can and should.
yeah, and I think we should view this as more than just a question of money. Money is sort of like an ethereal thing, but it's really the amount of effort. You have a certain amount of effort, in terms of people and machines, and depending on how efficient that effort is, for a given amount of effort, you want the most amount of batteries. So it's not just a question of like, well, if we had $2 trillion, tomorrow you could make this. It's not that easy. You actually need to organize a massive number of people, build a lot of machines, build the machines that make the machines. And so it's incredibly important to have that effort yield the most number of batteries. So, and then goal two, obviously, we need to make more affordable cars. I think one of the things that troubles me the most is that we don't yet have a truly affordable car, and that is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down. We've got to make, and we've got to be better at manufacturing, and we need to do something about this curve. The curve of the cost per kilowatt hour of batteries is not improving fast enough. So we've given this a lot of thought over many years to say, okay, how can we radically improve the cost per kilowatt hour curve? It's been somewhat flattening out, actually, in recent years. So
early growth was promising, but you can see we're kind of plateauing. Yeah. So that's what's motivating us to rethink how cells are produced and designed.
Yeah, exactly. And EV market share is growing, but EVs, still aren't accessible to all. And you can see, as Drew was saying, it's like starting to flatten out a little bit because the rate of improvement of the affordability of cars is just not fast enough. So that's why we got Battery Day.
Yeah. To make the best cars in the world, we design vehicles and factories from the ground up. Next.
Yeah.
And now we do this for batteries as well.
Yeah. It's weird, the slides don't show up quite right. Anyway, what shows up on the screen is not quite what shows up there. Anyway.
Oh, okay.
It's different.
Yeah, I think it's because that's, yeah.
No, that one's current, supposed to be current. Anyway.
So let's get started. We have a plan to halve the cost per kilowatt hour.
Yeah.
And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. And we're going to go through that plan with you today, step by step, and build up how we get to these goals and how we accelerate this transition and make our vehicles and our grid batteries more affordable.
Yeah. I mean, we basically thought through every element of the battery, well, almost every element. There are a few more elements that we won't get to today, but we will get to in the future.
Yes. So first, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. So it's quite a long winding process. And you can see the tab still there. And then To explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we, there we go, discharge the cell. Got lithium moving from anode to cathode, and then the reverse. When we charge the cell, anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, whether they're no matter what the form factor is. And when we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future.
Yeah. Actually, so a slight note on why is the one called the 18650, although not on the slide, versus the 2170, is that the first two digits refer to the diameter, and the second two digits refer to the length. So that helps explain why are these weird. What's up with these weird numbers? But like nobody could explain to me why there was an extra zero. So I said like, okay, well we're deleting the zero that nobody can explain in future form factors. So that's why it's technically it's like the 18650 bizarrely, but going forward it's the 2170 because we just got rid of the extra zero because it's pointless.
And this was a evolutionary step, going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at us in front of us, and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like anybody could make a bigger form factor.
Any fool could make a bigger form factor. We not any fool.
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about, that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
Yeah, that's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is, again, like this is quite hard to do. So it's nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a freaking tabless cell and have it actually work and then connect that to the top cap. And it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything. But
sometimes what's elegant and simple is still hard, and it took us a lot of trials, but we're happy where we ended up.
Yeah, I mean everything's simple in recollection. After you simple, everything it's hard until it's discovered, and then it's simple. So anyway, but there's a lot of really cool things going on that enable tabless, and it's really due to a really great engineering team. Drew and the rest of the team have done amazing work in achieving this tabless construction. And it sounds, I think it may sort of sound a bit silly to some people, but this is like, if for people that really know cells, this is a massive breakthrough.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating.
Yeah.
And has an awesome thermal and performance benefit.
Yeah, that's just to elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then sometimes you get the tabs wrong. And you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
Yeah, so when these... yeah, it's pretty great. And just to clarify that when we see these plus 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So this is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry, where from humble beginnings, over a century of innovation has enabled mass-scale, continuous motion, unbelievably low manufacturing cost. And when we think about the lithium-ion industry, which is really only in its 3rd decade of high-volume production, it has so far to go to achieve similar scale and simplicity. And that was the inspiration that we set out to the team as we thought about how to marry cell design and manufacturing in the best possible factory. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time, and where the sort of the electrochemistry is set and the quality of the cell is verified. And we set out at every step of this process to try to take that inspiration we just showed and think about how we make those processes fundamentally better and more scalable. And one of the most important processes is where it all begins, the wet process of the electrode coating. And just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing, where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven, where the slurry is coated onto the foil, huge ovens, tens of meters long, dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. This is serious iron involved in making batteries. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat? And that's what the dry process really is about. And in the most basic form, you can see it here on a bench top. Literally, powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, you know, if this was easy, everyone would do it. So it's not like dry coating electrode is actually easy. It's actually very hard to do what appears to be a simple thing. And it's worth noting, like, you know, we did acquire Maxwell as like a little over a year ago, I guess. And you know, it's certainly a good company and everything, but the dry coating they had was like is like sort of I would call proof of concept. Since the acquisition, we've actually revved the machine that does the dry coating 4 times. So we're in revision 4 post acquisition of the machine, and there's still a lot of work to do. So I would not say this is like completely in the bag. It's still a lot of work to do, and you know, as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you know, you make something work on your bench and bingo, now you can make a bazillion of it.
Absolutely.
It's insanely difficult to scale up.
Yeah, but if you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be clear, I would like to not say that right now it's just totally working. It's close to working, but it's not, even now at the pilot plant level, it is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah.
So
we're still ironing out the kinks, but we've made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way. Yeah. I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yep.
So, but this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production. The rate at which the machines are being improved is extremely rapid. Like literally every 3 or 4 months is a new rev.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
I want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, 1 line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having 1 line be 7x the capability is just effort multiplying.
Yeah. So. Yeah, you can sort of think about like the sort of the fundamental physics of a factory or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation you've got your exhaust velocity and then the log of the start to end masses. So it's basically saying, you know, how fast are things going and what percentage of the factory volume is doing useful work, and conveyance does not count as useful work. So
only the value-added steps.
yeah, if you break the factory down into cubic meter sections, and say or smaller, it could be like 1 liter sections, and say is a majority of this volume doing useful work, you would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. So I think it is possible to get to at least 10 times that volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory. It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to two factories basically, and the company that will be successful is the company that with one factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we with one factory achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Hybar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps.
Yeah, I mean, basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible. But I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to
Yeah.
solve. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
So.
You want to take this one?
Sure. So essentially what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. We're able to, from a volume standpoint, actually get what, in a smaller form factor than Giga Nevada, we were able to get many times the cell output. So you can see, like, basically we can get a terawatt hour in less space than it took to make a gigawatt hour, 150 gigawatt hours. So this is pretty profound. It's like, I would actually not have thought this was possible several years ago. That we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours.
Yes, simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission. And as Elon said, we're going to try to even improve on this as we push towards our goals, which are.
Yeah. So this is just for. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. And so this is 100 gigawatt hours supplemental to what we buy from suppliers. And yeah, essentially, this does like reduce our weighted average cost of a cell because but it allows us to make a lot more cars and a lot more stationary storage. And then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we can. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
When you look at the size of that factory on the previous page, it really shows how enabling all of these advancements are in achieving a 3 terawatt hour goal by 2030. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
But wait, there's more.
Yeah.
So we have a manufacturing system. We've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically, with silicon, the cookie crumbles and gets gooey. That's basically what happens.
Good analogy.
Yeah.
And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials in the scheme of things. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. And you can see some of the things that maybe you've heard of, SiO, silicon with carbon, or silicon nanowires. I mean, that's kind of the space right now. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
Yeah, I'm not sure if you saw this. Basically, $1 per kilowatt hours.
Yeah.
Basically, if you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour.
Yeah.
And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. Cobalt is a...
Yeah, sorry, I was just going to say, like, it's tough to exactly figure out what the right analogy is to explain cathode and anode, but a bookshelf is probably a pretty good one in the sense that you need a stable structure to contain the ions. So you want a structure that does not crumble or get gooey, or basically that holds its shape in both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. So if it doesn't retain its structure, then you lose cycle life and your battery capacity drops very quickly.
Absolutely. Yeah, I totally agree. And I think people are always talking about like, oh, what's the cathode going to be? Is it NCA or whatever? You know, the thing to consider is just fundamentally what the nickel, the metals are capable of, and that's what we have on the chart here. $1 per kilowatt hour cathode of just the metal, using just LME, you know, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode $1 per kilowatt hour.
Yeah. It's a big deal.
But it's not just about nickel. You want to?
Yeah, sure. So in order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. But there's also, I think we need to have a kind of a 3-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long range applications like Cybertruck and the semi. Because something like a semi truck, it's extremely important to have high energy density in order to get long range. So, and just to give sort of iron a bit more time, like although if you look at the watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you fully considered at the pack level, everything else taken into account, nickel is about maybe 50 or 60% better than iron. So iron is a little better than it would seem when you look at it at the pack level fully considered. It's not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. And so, good for stationary storage and for medium range applications where energy density is not paramount. And then, like I said, for intermediate, it's kind of a nickel manganese. And it's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off. I mean,
Yeah.
Just enough to have you still want to use 100% nickel for something like a semi-truck, but really not much of a sacrifice at all.
Yeah.
And, beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode $1 per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. Here's a view of the traditional cathode process. Effectively, if you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that's just happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproducts.
Yeah, it's insanely complicated. If you look at the total, like if you're just like, it's a small world journey of I am a nickel atom. What happens to me? And it's crazy. Like you're going around the world 3 times. There's like the moral equivalent of like digging the ditch, filling the ditch, and digging the ditch again. It's total madness, basically. And these things just grew up as they're just kind of like legacy things that it's like how it was done before. And then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. Much more scalable solution.
Yeah.
And then when you think about the fact that now we're actually just directly consuming the raw metal nickel powder, it dramatically simplifies the metal refining part of the whole process. So we can eliminate billions in battery-grade nickel intermediate production. It's not needed at all.
Yeah.
And we can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean, to be clear, cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
And on that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
Yeah. So it's important to note that there is a massive amount of lithium on Earth.
Yeah.
So lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Like all the cars in the United States, there's like 300 million or something like that. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States.
Discovered today.
What we already know exists.
People really haven't even been looking.
Yeah, people haven't been trying because it's just like widely available. So, but it is important to say, like, okay, what is the smartest way to take the ore and extract the lithium and do so in an environmentally friendly way? And we actually discovered again, looking at a sort of first principles physics standpoint, instead of just the way it's always been done, is we found that we can actually use table salt, sodium chloride, to basically extract the lithium from the ore. Nobody's done this before. To the best of my knowledge, nobody's done this. And it's a sort of, all the elements are reusable. It's a very sustainable way of obtaining lithium. And we actually we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before, and it will not look like terrible, and yeah, it'll be nice. Nice.
Yeah.
So
simply mix clay with salt, put it in water, salt comes out with the lithium, done.
Yeah, it's pretty crazy.
Yeah. So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet.
Yeah, that's true. Actually, just what's in Nevada. That's basically so much damn lithium on Earth. It's crazy. It's one of the most common elements on the planet.
And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why.
Yeah.
The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since we know our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
Yeah, and just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But eventually, it is the way that all resources will be made available, and that's why we're investing in this recycling facility in Nevada.
Yeah. Long-term, new batteries will come from old batteries once the fleet reaches steady state.
Right. Okay, so we just talked about scaling cathode and recycling. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
Great. So there's an architecture that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's a great achievement of our materials team. In fact, in general, we've got a lot of advanced materials coming for Tesla, that new alloys and materials that have never existed before. So so you're basically making the front and rear of the car as a single piece, and then that then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were like basically worse than cargo. You had to kind of bolt them down. It was very difficult. And then somebody said, "Hey, what if we just make the wing tanks? What if we just make the fuel tank in wing shape?" So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. What we do is essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat, and you have carbon fiber face sheets and say aluminum honeycomb between them, this gives you incredible stiffness. And it's really the way that any super fast thing works is you create a basically a honeycomb sandwich with two face sheets. This is actually even better than what aircraft do, because aircraft do not do this. They can't do this because fuel is liquid. So in our case, the batteries are solid. So we can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car.
Yeah.
In fact, if this was like a convertible that had no upper structure, it would be stiffer than that convertible would be stiffer than a regular car. So this is it's just really it's really major. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of have to, you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to use to move the cells closer to the center of the car, because we don't have the in the top one we've got that sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that you can think of like when there's ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't want to know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. So, I mean, I really think that long term, in any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal. It's casting machines. It's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Yeah, so it's major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah. Yeah.
All right, so stacking it up, we're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. So I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah, just happened to happen out that way. Yeah.
I mean, 0.420%, of course. So what this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So, you know, it's not like if we could do this instantly, we would. But it's really, I think what this bodes for, it just really bodes well for the future, and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. So, you know, what tends to happen as companies get bigger is things tend to slow down. Well, actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
Yeah. I mean, long term, we want to try to replace about, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter where you are in the value chain, there is a ton to do. You need to rethink from first principles how you do it so that you can scale to meet all of our objectives.
Yep.
And Elon?
Sure.
What does this mean?
What does it mean for what does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it because our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a, I don't know, mass market premium, but like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah. So we have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that? Yeah. Woo. So, anyway, we took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. So we're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise. And you can order it now, and it's available basically end of next year. So, and now we'll move to Q&A.
Absolutely.
So we'll invite a few people on stage.
Come on up, team.
So this is just a small portion of the team, but it would be great to show you some more of the team, and when we do Q&A, we can give various people different questions to answer.
Sounds great. Actually, I don't know how we're getting the questions.
Actually, I don't know either. Is somebody going to read them to them? Okay, well, you could just you can maybe get out of the car for 2 seconds and yell it at us. I don't know. Hey, how do we get the questions?
Oh, they're mics. Okay, wait for the mic.
Oh, there are mics. Okay, great.
All right.
Okay, we'll definitely need to give people mics because otherwise there's no way. Sorry? All right, we're gonna pass some mics out. We don't have a name for the $25,000 car yet.
It's a great question, though.
Yes, we will be manufacturing cells in Berlin. Yep.
Thermal management system? For homes.
Oh, you mean like the home HVAC? Yeah, I mean, that's a pet project that I'd love to get going on. I don't know, maybe we'll start working on that next year. Because I just think man, you could really make a way better home HVAC system that's really quiet and super efficient and super energy efficient, and also has like a way better filter, for particles, and and it works very reliably. And we've already developed that for the car. Like, so the heat pump in the Model Y is really pretty spectacular. I mean, it's tiny, it's efficient, it has to last for 15 years. It's got to work in all kinds of conditions, from the coldest winter to the hottest summer. So we've actually already done a massive amount of the work necessary for a really kick-ass home HVAC. And they could also like stack them. So if you want to say, depending upon the size of your house or whatever, how much you need, you can just basically stack them, and just have a very compelling, super efficient home HVAC. And then you can also communicate with the car, and it'll know when you're coming home. So it's like, oh, I don't need to keep the house cold all day. I just cool it down because I knew you were coming home. So the pack can communicate with the car and just like really dial it into when you actually need cooling and heating. It'd be great.
Fun product.
Yeah.
Who's next?
Hello. Hey guys, Eli here from Tesla Owners Club, My Tesla Adventure. Just quick question. So I'm a huge fan of car camping in my Tesla with my dream case, like my all-time favorite activity. Is it going to be possible to get climate control to the back of the Cybertruck? Because that would be the ultimate camping machine if we can get all-night climate control.
We'll try to do that. Yeah. I agree. That would be really cool. Yeah.
All right, who's next?
Hello.
Yeah.
Long-time fan, Elon, great guy. Just a question. How does the ICE industry look like for in the future?
Well, I don't think there will be an ICE industry long term. So, yeah. I mean, well, I guess there might be like a few things that are like, it's a like curious thing. Like, I mean, there's still like some steam engines made somewhere, but like they're just basically sort of quirky collector's items. I mean, that will be the future of the internal combustion engine car.
Hi, Elon, to your left here in the white Model Y. Ryan McCaffrey from the Ride the Lightning Tesla podcast. Curious about Cybertruck. It was interesting to see where you had it in on the battery technology front. I'm sort of curious what you see for it in the production front. Is its volume, trucks are so popular in America, do you see its volume equaling the 3 or the Y in the future? And also, is were you able to get Tesla is able to legally be sold in Texas as part of the Giga Texas deal?
Well, it's hard to say what the volume exactly would be for the Cybertruck. The orders are gigantic. So we have like, I don't know, well over 500,000 orders. I think maybe 600,000. That's a lot, basically. We stopped counting. So I think there's probably room for, I don't know, at least like a unit volume of like 250 to 300,000 a year, maybe more. Now we are designing the Cybertruck to meet the American spec, because if you try to design a car to meet the global, the superset of all global requirements, it basically, you can't make the Cybertruck. It's impossible. It really is designed for the American market, but this is the biggest market. Our North American market is the biggest market for pickup trucks by far, or large pickup trucks. And then I think for we'll probably make an international version of the Cybertruck that'll be kind of smaller, kind of like a tight Wolverine package. It'll still be cooler, but it'll be smaller because you just can't make a giant truck like that for most markets. So yeah, but it's gonna be great. And I don't know. I think probably we'll be able to sell directly in Texas. We do pretty well right now, but it is a bit weird not being able to actually conclude a transaction in Texas. But it's got to be like a click on a server based in California. So, but weirdly we can do leasing in Texas, but not selling. But hopefully that'll get cleared up in the future.
Yeah, Elon, great job with everything that you're doing. Thras Gerber from Gerber Kawasaki, your team's amazing. What I'm most curious about, these innovations are incredible, but on my drive up here, fully on autopilot for 400 miles, the entire state is brown, and this is ultimately about climate. Has there been some analysis done if all these things are achieved? What will its direct impact be on climate?
Well, I mean, I think it will have a very significant impact because it will stop the CO2 ppm from growing as it is every year. And I mean, I should say, like, I try to view the whole climate thing for as a science question as much as possible. Science, you always question your hypothesis: is it true? Is it not true? Or assign a probability to a given hypothesis. And I should say that my original interest in electric vehicles predates the climate issue. Like just when I was in high school, I thought, man, if we don't figure out electric cars, the whole economy is going to collapse when we run out of oil. So it's like, we better figure out electric cars and sustainable energy, or civilization is going to crumble. And then it was only kind of later that the significance of the climate risk became apparent. We were also able, using fracking and other types of technology, to access a lot more fossil fuels than previously thought, which is, helpful for lowering the cost of gasoline, but it's pretty bad for the total tonnage of CO2 that you could put in the atmosphere. It's now greatly beyond what people previously thought. So, but this is, as we were just going through in this presentation, it's like it is a absolutely monumental task to accelerate the advent of sustainable energy. I mean, the entire global economy is still, more than 99% dependent on, or roughly 99% dependent on fossil fuels. So although electric cars kind of get a lot of press right now, they're still, and there's still very few, as a percentage of the total global fleet, is practically nothing. I would say, yes, less than 1% of the global fleet is electric right now. Because of 2 billion cars and trucks and whatnot in use. So there's a massive amount of work ahead, just insane, like hard to comprehend how much work is ahead to get the new vehicle production to be sustainable, to massively increase the amount of stationary storage, which is critical because renewable energy is intermittent. Wind and solar is intermittent. Sometimes the wind doesn't blow, and obviously the sun doesn't shine at night. So you got to have batteries, a massive number of batteries. So
it's hard to measure in direct impact, but it's an experiment that we shouldn't be performing, and the sooner we can sort of end the experiment, the sooner we can kind of move on in a fully sustainable way that is actually lower cost. I mean, I think the thing that people haven't fully internalized is once we do get to the 25K car, the ownership cost of that car is incredibly lower than the prior car. And then on the solar side and wind, with the cost of solar and wind coming down and with batteries coming down with them, the actual cost of energy on the grid is going down. So we're sort of moving towards a sustainable, lower cost future. So there's not really a sacrifice.
Yeah, that's true. It is a false dichotomy to say that it's either prosperity or sustainability. This is often used, by oil and gas to say like, oh, well, do you want people to lose their jobs? Do you want lower people's standards of living? Do you want to, make all these economic sacrifices, really, in order to have sustainability? And the reality, as Drew was saying, is that a sustainable energy is going to be lower cost, not higher cost, than fossil fuels.
Elon, quick question for you, right here in front. First, thanks for having everyone, and as telling a friend, the one company to go work for that's going to have the biggest structural impact over the next 10 years at scale, it's probably Tesla. So kudos to everyone at Tesla for what they've done to this point and going forward. The two questions for you, as you've looked at the auto and the storage markets, I know you've talked about it at kind of 50-50 long term, but it seems like a lot of the battery cost curve achievements that you've presented today really make some of these storage opportunities much more feasible over the next 5 years. And so I guess the first part of the question is, does your calculus upon learning and improving these things change on that 50-50 mix, or is there a role where storage becomes bigger? And then the second part of the question, with all these huge grand visions, who's going to be with Tesla from a corporate perspective accomplishing these things? Obviously, Tesla can't do it alone, but when you look at some of the traditional auto industry or power, et cetera, I don't see a lot of other Teslas.
Well, actually, so there's a lot of companies in China that I think are doing great work with electric vehicles and also with stationary storage. Although we don't see that much in the US yet, but I think probably we will in the future. I don't know. I mean, obviously, we're doing everything we can to encourage other companies to move to sustainable transport and also, make stationary storage batteries. We opened up, made our patents freely available. We really try to tell these companies, hey, you really need to do this or you won't exist in the future. But they don't believe it, So, I mean, we've talked until we're blue in the face. What are we supposed to do? But we really are hopeful that other companies will also do what we're doing, and that will make a sustainable future come sooner.
From a fundamental market size perspective, like we did the first ground up work to show the size of the market in terawatt hours, and they are roughly 50-50. 10 terawatt hours for transportation, 10 terawatt hours for the grid. And part of that is because the grid batteries, because when you're making a power plant, you're making a large investment, are 25-year assets or greater. If the grid batteries were 10-year kind of things, the grid market would be bigger, but because it's a longer duration asset, they're roughly the same size.
Thinking long term, is there any other segments that this new battery will be able to disrupt or electrify beyond just the initial Model 2 or cheaper sedan, like a boat, boring company, Luke, plane, boat?
Where are you, Golly?
Are you
there?
What's up? Right here.
Okay, great.
It's
like ventriloquism here. It's like we just get the sound out of the speaker and you can't tell where the heck it's coming from.
Yeah, any hints, or is the Model 2 such a big deal because it decreases the cost of transportation that is really the disruption? Or should we get hyped that this new cost curve opens up different vehicle categories like a high passenger density bus, boring loop, boat, plane?
I mean, there are batteries in limited production right now that do exceed 400 watt-hours per kilogram, which I think is about the number you need for decent range, medium range aircraft. I think our batteries will, over time, start to approach the 400 watt-hours per kilogram range as well. I mean, I think over time we'll see all modes of transport, with the ironic exception of rockets, transition to sustainability, or to electric, basically. On the rocket front, what we're planning to do is about 80% of Starship is liquid oxygen, and we're actually already running a power line to be able to use wind power to create the liquid oxygen. So we're making some decent progress on sustainability on the rocket front, but there's just no way to have an electric rocket, and it's important for the future of life and consciousness that we become a multi-planet species. So got to keep doing that.
Hi, Elon.
Hello.
Josh Phillips here, retail investor. I have a question in regards to the lithium and nickel industries and the likely price spikes and shortages of high-grade materials the EV industry is likely to see if they don't act fast to address future supply. Tesla have clearly made the right moves that are necessary, but there's a real worry that the potential supply issues and price spikes will create a drag on the rest of the EV industry and therefore a drag on global EV adoption. What advice would you give to the EV and mining industries to quickly solve this looming hurdles? Because for a sustainable energy future, the spice must flow. Thank you.
Yeah, indeed, the spice must flow. The new spice. I don't know. I think I'm not sure. I guess we can try to like basically overdo it in cell production and perhaps supply cells to others. But we do see the fundamental constraint as total cell production. That's why we're putting so much effort into making cells and kind of trying to reinvent every aspect of cell production from mining the ore to a complete battery pack. Because it's the fundamental constraint. We're not getting into the cell business because we, just for the hell of it. It's because it's the fundamental constraint. It's the thing that is the limiting factor for rapid growth. But we could certainly try to overdo it on cell production and perhaps sell cells to others. Although we are going at absolute top speed, so it's not like we're holding it back. But I think just making really efficient cars and that have lower drag coefficient, low rolling resistance, efficient powertrains. That's kind of what we've done in order to make iron phosphate still have a good range. So the iron phosphate's lower energy density solution, but there's while there are some limitations on the total amount of nickel produced every year, there's really no limit on the iron. There's so much iron, it's ridiculous. So you can really scale up iron phosphate, at a raw materials basis faster, more than you can nickel. But yeah.
And just to point out, when we were walking through this presentation, we intentionally separated all the different aspects. The benefits of structural battery apply to a iron-based cathode in the same way they apply to a nickel-based cathode. Yeah. So you get longer range iron-based vehicles, and also the silicon benefit can apply to the iron-based vehicles as well. So we can do a lot to extend the range of an iron-based vehicle, which is why it's a key part of the roadmap going forward. And then I invited Turner up here to talk about what the mining industry can do.
Yeah. Diversification on the cathode side is obviously massive, and EVs are all about efficiency. And so for the EV industry, for the vehicle industry, we need to see powertrain efficiency really increase at all other companies matching Tesla powertrain efficiency so that everyone can have that diversified cathode approach where LFP is used in medium range and even really make a 300-mile vehicle with LFP. And really the goal that we were trying to present here was a model for vertical integration, strategic vertical integration that a lot of different people can do. What we need to see is vertical integration that shortens the process path from mine to cathode. And what we're doing here is novel, and we're trying to push the industry in that direction. So we're presenting a model here that anyone can follow.
Yeah, in fact, if there's anything that you guys want to comment on, feel free to step forward and say something.
I think the key is to be smart about your chemistry choices, your materials choices.
Talk louder.
Yeah, if you're smart about your materials choices, the spice will continue to flow. Yeah. You don't need to use the same kind everywhere, and it's about strategically planning it out. And for miners, I think we are incentivizing them quite a bit to ramp up their production.
Yeah, and actually we had good calls. Like they're all motivated. I think that they've been sort of sitting back, being like, "Are you going to grow like crazy?" And we're like, "Yeah, we're going to grow like crazy." And then I think this indicates we're going to grow like crazy, and that's what the miners want to hear. And then they'll go make the investments.
Hello, Elon. This is Ben Limpick. I'm a musician. I was wondering, does Tesla have any future plans to make partnerships with music companies like it has done with 10-cent games or things like that for you guys to actually kind of expand your services for artists and other types of creative people to get involved in producing content that can be part of the Tesla ecosystem, or so other people that do creative things can get involved with you guys?
Well, we don't. We haven't really thought about that much, but I suppose it's probably something we should think about. We will be providing a title on Teslas. So we're providing more music sources that people can choose from, and generally trying to improve the entertainment experience in the cars. And I think actually as we go to a more autonomous future, the importance of entertainment and productivity will become greater and greater. I mean, to the degree that if you're just basically sitting in your car, the car is fully autonomous and driving somewhere, it's sort of like being in a, you know, the car is essentially your chauffeur, and then the things that become important are, okay, well, let's have good entertainment, and you know, if you want to do some productivity stuff, then that actually starts to become much more important because you're no longer spending your attention driving the car. So it will be extremely important in the future.
Should we do some of the say.com questions? Yeah. Okay. Should we do the second one?
Yeah. The first one I think we already answered. Like if we're able to make enough cells, which we'll try to do, or we will supply other companies. It's definitely not an intentional effort to keep the cells to ourselves. If we can make enough for other companies, we will supply them. And we're trying to do, you know, the right thing for advancing the sustainable energy, whatever that is. So, vehicle to grid, we get asked that a lot. I think one of the things that's important to note is the vehicle to grid. It doesn't, unless you have a power cutoff. Like you need to cut off your main supply to the grid. Otherwise, if you lose the power in your house, you'll basically just backflow energy to the grid. So just having a reversal in the power flow does not actually keep the lights on. You need a whole separate system to cut off power to the grid. And I think there's also the case that people really want the freedom to be able to drive and to charge at their house. And it's obviously really problematic if you know, you get to morning and your car, instead of being charged, it discharged into the house, and then you're sort of, okay, now I can either drive or use the battery to power my house. I think it's actually going to be better for people's freedom of action to have a power wall and a car separate, and then it's you know, everything works. You know, and you add that, you basically combine that with solar, either solar retrofit or solar glass roof, and local battery storage. So you basically become your own utility, and then the car is you know, can be charged also with solar. I think that's like the stuff that works. You know, that said, like we can certainly do vehicle to grid. I think we could basically enable that with software in Europe or something, right?
Yeah. We are future generations of power electronics. We will be able to do this more or less everywhere from a like energy market participation perspective. But yeah, from a backing up the house, and it just so happens that the way the North American connectors are on all the cars in North America, it doesn't matter whether it's the Tesla connector or the connector that the other vehicles have, doesn't actually support powering your home. It's unfortunate. So you'd need an additional hardware to do that. But yeah, in the future, all versions of our vehicles will be able to at least do bidirectional power flow for the purposes of energy market participation. But even for that, it's important to remember that your car isn't plugged in 24/7. So it's kind of an unpredictable resource for the grid. It'll have a value, but it's not the same as a stationary battery pack.
Yeah, honestly, a vehicle to grid sounds good, but I think actually has a much lower utility than people think. I think very few people would actually use vehicle to grid, and we actually had that with the original Roadster. We had vehicle to grid capabilities. Nobody used it.
Yep. How do we find the engineers to do everything we're saying?
How do we find the engineers to do all these things? I guess we recruit a lot of engineers from all parts of the world. You know, I think Tesla has a good reputation for doing exciting engineering, and that tends to attract a lot of the top engineers in the world, because they know that their efforts at Tesla will really serve the greater good, and we're super hardcore about engineering. You know, Tesla is like first and foremost an engineering company. It's like hardcore engineering is what we do. Like the sheer amount of hardcore engineering done at Tesla is insane. And if you look at, say, there's various surveys done of engineering schools, where do you want to go? Like, what's your top choices? And actually, the top two choices last last few years have been Tesla and SpaceX. So sometimes it's Tesla first, sometimes SpaceX first, but those are the two top ones.
Yeah, I mean, if you are motivated to solve some of these problems, which are the hardest problems in the world to solve, that really fundamentally enable the future we all need, please reach out.
Yeah, and
help us work on these problems.
Absolutely, and like you said, the battle is far from over. Less than 1% of the global automotive fleet has been converted to electric, and even maybe less than 0.1% of stationary storage has been done. So stationary storage has barely begun. Converting the global vehicle fleet to electric has barely begun. So there's still a massive amount of engineering work to be done at Tesla and other companies to accelerate this transition to sustainability.
Hey, can you guys hear me?
Yeah.
This is Jordan from Mark Asset Management. So you've talked about the importance of the factory, and you've mentioned the ground-up design process and a lot of the new things that you're going to be doing or started to do in Shanghai, Berlin, and Austin. Can you just maybe help us understand and quantify like how financially meaningful all of those improvements will be? And then given what you're trying to accomplish as a company, is it fair to assume that the vast majority of improvement will be given back to the customer in the form of lower prices?
Yeah, I mean, I think certainly we will try to give back as much as possible to the customers. It's not like, it's not like Tesla's profitability is crazy high. Our average profitability for the last 4 quarters is like maybe 1%. So just to be clear, it's not like, we're minting money. Our valuation makes it seem like we are, but we're not. We do want to try to make the price as competitive as we can without like losing money. And if you lose money, then if you keep losing money, you'll just die. So we have to. This thing called profit is just like we need to bring in more money than we spend, otherwise we're dead.
But affordability is key to how we scale,
Yeah.
right? Like the demand goes nonlinear as you reduce the price of the car.
Yeah, it's important to sort of separate the difference between affordability and value for money, or desirability of the product. So, for a lot of people, they want to buy a Tesla, they simply don't have enough money. We could make the car infinitely desirable, but if somebody does not have enough money, they can't buy it. Sometimes, people, kind of forget this. It's like, it's like people have to have enough money to buy the car. And just making a car super desirable but expensive does not mean they can afford it. So it's absolutely critical that we make cars that people can actually afford. Yeah. So I wish we could go some of these things. Just scroll down or something. Oh.
When do you expect Tesla vehicles to beat ICE vehicles on initial purchase price? I think a way to answer that question is, in the classes of vehicles we sell today, we're already doing that.
Yeah, we're already pretty close. And then factoring in total cost of ownership, the fact that electric vehicles require much less servicing, and are way cheaper to run. When you look at like total cost of ownership, and you can obviously lease a car. So if you just like lease a car or get a loan for a car, you've got your sort of monthly payment, and then your cost for either gasoline or electricity, and your cost of servicing. And the fully considered cost of an electric car is much less than a gasoline car of the same nominal purchase price. I mean, that said, and like maybe on the order of 3 years, when we can do a lower cost car, like a $25,000 car, I think that will be basically on par, maybe slightly better than a comparable gasoline car. So I think maybe it's on the order of 3 years-ish.
How have the technology advancements and increased vertical integration of battery manufacturing influenced your ability to improve the environmental and social impact of the supply chain? And I think, yeah.
I think we sort of have said that already.
Yeah.
Do you have some ability to scroll through this? Just scroll away.
We covered recycling.
Yeah. Well, just scroll until we've got stuff that we haven't covered.
Well, we definitely covered that top
yeah,
one.
a lot of the things we've already answered, I think.
Covered that. That one. I think
we literally just answered that.
Yeah. Oh, I saw a cathode durability question. Let's go to that one. Go down, go down, go down. Good technical question. Keep going. How are you going to address the cathode durability and cost and environmental impact trifecta? Is this something you're going to leave the upstream supply chain to solve? No, I think we tried to answer that directly. I mean, we really are looking at not just what happens in the cathode facility, but like currently outside the cathode facility that should really be inside, and removing processes that shouldn't have been there in the first place, and the use of reagents that are just costly and not necessary, and removing a bunch of wastewater from the process.
Guys, is there anything you want to add to? Maybe we could like go through everyone and like maybe say what you're doing and say a few words. I don't know.
Sure. I just want to reiterate the fact that this is a massive problem.
Massive problem.
And it seems like Tesla's on its way and ahead, but we need everybody's help because it's everybody's planet, and we're not going to get to 20 terawatt-hours by ourselves. So please think about this carefully as it affects everybody. So let's get on it.
Yeah. And obviously, if you care about solving sustainability and doing hardcore engineering, definitely come work at Tesla.
Yeah, we went through a couple of the manufacturing improvements, and it kind of looks easy when you put together a nice slide deck, but the challenges are like this. It's super challenging when you take materials out of the process, when you integrate processes together. You have to do a lot of things at once, and that's like this immense engineering challenge. And so, like, to appreciate that, like, you need, like, to get through this, we need, like, the best engineers we've got. And we've got this awesome team. I just want to shout out also to all of our team watching, like, you guys are awesome. Like, you absolutely kicked ass putting this together. And, yeah.
Yes. Thank you.
Thank you, Tesla team. Totally agree.
Yeah, that's it. Like, yeah.
Okay. Yeah. Rodney Westmoreland, managing the construction here at Tesla. What I would like to say is, one, shout out to the team. The team has been working effortlessly. A very, very tough project here for 24 hours a day, it seems like, around the clock to have this complete. The thing that sets us apart from a lot of other construction, we have a construction company here. The thing that sets us apart is that we're integrated in the manufacturing process. So every detail that comes from Drew's mouth is directly implicated into the system that we're building. That way, what would typically take 3 or 4 months to create a specification, our design team is working right with the manufacturing team to allow us to speed that process up tremendously. So.
Yeah, it's definitely a important part of the vertically integrated approach is to be able to design the factory around the equipment, in fact, together with the equipment, so that you can build the factory at lower cost and more quickly.